Happy Tuesday. Another wonderful week. So we just looked at vectors last time, right? We saw 2 vectors, 3 vectors, some basic operations. I believe we looked at what? Vector addition and scalar multiplication, right? Should have noticed that there was an operation that was not discussed, the idea of a vector product, right? Multiplying 2 vectors. Right now, just like subtraction is not a defined operation in mathematics, neither is division, right? So you actually only have 2 arithmetic operations, addition and multiplication, right? Subtraction is the sum of the additive inverse. Division is defined the same way. It is the product of the multiplicative inverse, right? So product of the reciprocal. As such, there is no such thing as vector division. You cannot divide 2 vectors. That does not make sense. You can take a product of 2 vectors, however, but you have to specify how, because there are 2 products. You have the dot product and you have the cross product. Dot product is also commonly referred to as a scalar product because the result is a scalar. Cross product is a vector product. The result gives you a vector. And this shouldn't be new to anyone who's taken a basic physics class, right? You should have looked at dot products and cross products in physics. With the dot product, there are several things we can do, right? So we can now discuss what we mean by an angle between vectors, right? We can also discuss vector decomposition, right? So oftentimes in physics in particular, you're interested in the force, right, along a specific direction, right? So force along a slope, for instance. Right? Or acceleration, what's known as centripetal acceleration. Right? This is all vector decomposition. So we take 2 vectors, right? In this case, A, and a vector that was not named that I'm probably just going to call B. Right? We want to find component of A that is parallel to B, and then the component of A that is perpendicular to B. Right? So whenever you decompose a vector, it's always with respect to a specific vector. So we'll say that'll represent the parallel component. Right, and that'll represent the perpendicular component. This is how you find the parallel component. It's the projection of the vector A onto the vector B. Well, that has a specific definition. What's the formula for projection? Yeah, go ahead. Want to take a shot? What was it?
U would be over U magnitude V.
You might be giving me something else. If you're saying U dot V over magnitude of U magnitude of V, then you're giving me the cosine of the angle between them. Right, so that's not, it's going to be similar. I'm going to use my other notation. Dot product. Is the dot product commutative? It is, right? B dot A dot B, same thing. So the order in which you take the dot product does not matter. What you have to be aware of, though, is the denominator. It's the magnitude of the vector that we're projecting onto, right? In this case, we're projecting A onto B, and then times the vector that we're projecting onto. I'm going to do this. I'm going to say, here's a formula you should probably remember. Right. My personal recommendation is formulas. I would write like on a separate sheet of paper, so you're not flipping through pages of notes trying to find the specific formula you want. Right. And you have a nice handy couple of sheets, whatever, at the end of the notebook, or have a whole separate notebook just for formulas. But that's entirely up to you. How do you find the dot product of two vectors? So how's the dot product defined? Yeah.
You just
Components. All right, so you multiply corresponding components and then what? Okay, so that is if you're going to use the formula U dot V is the magnitude of U times magnitude of V times the cosine of the angle between them. Right, so that is a way to do it. The problem with that is, what's the angle between A and B here? You'd have to actually use the formula U dot V over norm of U, which kind of defeats the purpose, right? So it wouldn't be helpful in this case. It's something very simple. Yes, you just add them together. So you multiply corresponding components and add them all together. Right, so Multiply the I components. Plus then the product of the J components, right? And of course, that naturally extends to if it's a 3 vector or a 4 vector or a 5 vector, right? You just keep multiplying corresponding components and adding the products. What is the magnitude of B? So what is the magnitude of 3i plus j? It's root 10, right? So we're going to square that. And that'll be then multiplied by 3i plus j. Now, of course, this is a defined operation, right? B dot A is a scalar. Magnitude's a scalar. So this entire piece right here is a scalar. So this is just a scalar multiplication, right? That is defined. Three times 4 is 12. 1 times 3 is 3. 12 plus 3 is 15. 15 over 10 simplifies to 3/2. There is our parallel component. Perpendicular component. Well, you just make use of the fact that the parallel component plus the perpendicular component has to actually be the vector itself. And so then the perpendicular component would be the original vector minus its parallel component. Four minus 9/2. Negative 1/2. And then 3 minus 3/2 would be what, 3/2? Right. So here's the parallel component. And there's our perpendicular component. So that would be our decomposition. Find the work done in moving the object along the vector 3i plus 4j if the force applied is 2i plus j. Right. So calc Calculus 2, you studied the idea of work. Right. In general, work is the force applied times the distance covered, right? Now that's of course one-dimensional. And your force is constant in the direction of motion. If your force is variable, but still in the direction of motion, it now becomes an integral. What if force is not in the direction of motion? If the magnitude of the force is constant, as it is in this case, it's just a dot product. And it'd be A dot B. If the force is variable, it is again an integral. More specifically, it's a path integral, which we will study towards the end of the semester. So it'd be revisiting work. Specifically, we look at what's the work that a force field applies on a particle moving through a path. Right, well, gravity is a force field. So whenever you're trying to calculate the force due to gravity, you technically should be doing a path integral. But we'll get to that. But for now, it's just a simple dot product, right? Right, work is always a scalar. And physically, work is energy spent. So how much energy you're expending applying this force moving a certain distance. Our force vector is 2i plus j. And then our path is 3i plus 4j. Two times 3 plus 1 times 4. Work done is 10. They didn't give us units, so we don't know what the units are for this. What would the standard units be for work? It's the joule. Right. What's the standard unit for force? Newton. What is the Newton equal to?
Kilogram times meter per second squared.
That's one. It's a kilogram meter per second per second. And of course, distance, position, standard units are meters. So the joule would be a Newton meter, which is a kilogram meter times meter per second per second. Given 2 points P and Q, asked to find the angle between the vectors OP and OQ. Right. So O always represents origin. So if we're looking for OP, right, that is the directed line segment from the origin. So it has initial point at the origin and terminal point at P. OQ is the directed line segment, initial point O, the origin, and terminal point Q, right? In other words, these vectors are in standard form. So the component form of the vector is just the terminal point, which is really nice. Angle between them, it was already mentioned. The angle between two vectors is given by cosine of theta equals the dot product of the vectors divided by the product of their magnitudes. What is the range of the inverse cosine? Is it inclusive or exclusive? It's inclusive, right? 0 to pi inclusive. The question becomes, would we be able to always take the inverse cosine and say theta is the inverse cosine of that quantity? All right. Another way is the angle between two vectors will always be between 0 and pi. Why do you say yes?
Because it can only be like 80 degrees one way or other. So it'd be like in terms of radians, it'd be either pi this way or pi.
Well, you're saying can only be 180 degrees, so you're saying that's the only possible thing, right? So 180 degrees would be this.
Right.
That's the only possible
No,
angle.
like it could be like in that range.
Right, so you'd say that's between 0 and pi, right?
Right.
What about that?
That's between 0 and pi.
Right, because you're not measuring the larger angle, you're measuring the smaller angle between them. So yes, it's always going to be between 0 and pi. 0 would mean they're parallel, they point in the same direction. Pi would mean they're parallel, pointing in opposite directions, right? What about pi over 2? What special name is that given for vectors? Orthogonal. Right, just a fancy way of saying perpendicular. There's a third way of saying perpendicular, by the way, when we deal with planes. Normal. Well, by the way, that gives us a nice way of determining whether two vectors are orthogonal. What is cosine of pi over 2? What is it? 0. Can the magnitude of a vector ever be 0? There's only one vector that has a magnitude of 0, and that's the 0 vector, which is essentially just a bloody point. Right, so it's not even a vector anymore. Non-zero vectors will always have positive magnitude. Remember, that's good, right? That means that our denominator will never be 0. So if cosine of pi over 2 has to be 0, that means the dot product has to be 0. So two vectors are orthogonal if and only if their dot product is 0. That does work both ways. If they're orthogonal, you know the dot product is 0. If you know the dot product is 0, then you know they're orthogonal. So for us, u dot v, we're going to have 2 minus 6 minus 3 over magnitude of u square root of 14 times magnitude of v square root of, looks like 14 again. Oh, that's nice. All right, 6 and 3 is 9, so we're going to have 2 minus 9. So negative 7 over 14, negative 1/2. That's what cosine of theta is. So theta would be the inverse cosine of negative 1/2, which is what? The angle between these two vectors is 2 pi over 3. Remember, angles always in radians. We're looking for this angle. And we're given the vertices. Well, that means that we're first going to need to know those two vectors, right? Little a and little b. How would you find the vector little a? Right, how would you do that? Why? No, but why did you choose A and C? It's the directed line segment with initial point A and terminal point C, right? So what is it? You said 1 and -1. What about B? How would you find B? Right, and why did we need those? Well, wouldn't cosine of alpha just be their dot product divided by the product of the magnitudes? Dot product. Be what? -3 -1 plus 0. What is the magnitude of A? What about the magnitude of B? That means we get -4/√22, right? So alpha is the inverse cosine of -4/√22, which is what? The answer is obvious. Wasn't a fair question. That can't be simplified. So it's the inverse cosine of -4 over root 22. Just leave it in that form. And remember, you do not approximate unless you're told to. Okay. Well, recall we had standard unit vectors, right? We had I, J, and K. What did I represent? Which is what in what's its physical interpretation or geometric interpretation? Remember, vectors also have a direction. So length 1, but what direction? In the x direction. So you can think of I hat basically as the x-axis. What about J? And what about K? Well, if you can think of those as vectors, then wouldn't there be an angle between that and a vector itself? These are known as the direction angles. You have alpha, you have beta, you have gamma. Alpha is the angle made with respect to the x, beta is with respect to the y, gamma is with respect to the z. You find them the same way. So cosine of alpha would be A dotted with I over the magnitude of A times the magnitude of I. Well, real quick, we can simplify this. What is the magnitude of I? You said it already. Magnitude of I hat. It's 1. It's a unit vector. So the denominator is just the magnitude of A. Take any vector, dot it with I hat. What is your result? It's just the x component, isn't it? So cosine of alpha would just be the x component of your vector divided by the magnitude of your vector. You can use similar arguments. to get cosine of beta and cosine of gamma. Now, these are direction angles, which means we're not measuring it with respect to the positive x-axis. Right. I guess technically we are, but we're not considering clockwise and counterclockwise. Right. So if you just think of the xy plane, if the vector lies below the x-axis, it would still be a positive angle. Right, because we're just going to go counterclockwise instead, or clockwise instead. So you can still take the inverse cosine of these angles, or of these formulas. Right, your angle should still be between 0 and pi. What is the magnitude of A? It's 13. And it's square root of 169. By the way, that 13 is going to be the same, right? For all three. So y component is 12. And the z component is 4. Then you just take the inverse cosines. And those are your 3 direction angles. So determine the value of k so that the 2 vectors u and v are orthogonal. Remember, we discussed this already. 2 vectors are orthogonal if and only if what? Their dot product is 0. Right. Take u dot v. Get 2 times 1 plus k times 3 minus 1 times 8. Right. So 3k minus 6. That has to be 0. Solve for k. Clearly, k has to be 2. Well, that was easy. Determine a unit vector that is orthogonal to both U and V. I'm just going to look at it general right now. So let's say there's U, there's V. A vector orthogonal to both of those. How many vectors are there that would be orthogonal to both of them? Just two? How do you get two? Okay, I agree with that. So I'll ask again, it's only two vectors. It's not two. There's an infinite number. Remember, a vector is both magnitude and direction. If two vectors have the same direction but different magnitudes, they are different vectors. So you have two directions, right? In this case, you have out of the screen or into the screen, but in each direction, you have an infinite number of such vectors. But we can simplify that because we're asked for unit vector. Now there's two. Right, you have a unit vector out of the screen and a unit vector in the screen. So if this was just specifically saying, determine a vector orthogonal to both, I would determine a unit vector. I would determine the two unit vectors and then say any scalar multiple of those two would be a valid answer. I could be particularly evil and say find all vectors orthogonal to both. That would be fun. Right. So we're asked for a unit vector, so it doesn't matter whether you find the one that's coming out of the screen or into the screen. Again, for this specific example, both would be valid answers. Right, but the point is, get your minds out of the gutter. We want to find so I immediately know who has a vulgar mind. Want to find a vector W just to start. Right, we can convert it to a unit vector later. Such that U dot W is equal to 0 and V dot W is equal to 0. There is a simpler way of finding this, but we haven't studied that operation in this class yet, so we don't get to use it. So yes, we're gonna have to do this the hard way. So let W be some arbitrary 3-vector, right? Just call it X, Y, Z. Right. Our goal is to find X, Y, and Z. Take U dot W. Two X minus 6Y minus 3Z, right? We want that to equal 0. Now take V dot W. 4X plus 3Y minus Z. We want that to equal 0. This is a linear system of 2 equations and 3 unknowns. Such a system has 2 outcomes. Either no solution exists or an infinite number of solutions exist. So either there is no vector perpendicular to both of these, or there's an infinite number. Well, that satisfies the idea that we discussed earlier, right? That there's an infinite number of vectors perpendicular. So either we're going to find no such vector, which is a possibility. It's a very rare possibility. In 3 space, though, it's guaranteed. Right, so since we're only dealing with 3 vectors, we're given 3 vectors. We can find a vector perpendicular to both of them in space. That's guaranteed. So there's going to be an infinite number of solutions, which satisfies, again, our condition. Then we just take a unit vector, right? So we have to solve this system. Bless you. There are 4 methods for solving a linear system. One method is systematic elimination, which you studied in algebra. Then you have Gaussian elimination and Gauss-Jordan reduction. That requires linear algebra. The 4th technique is my personal favorite. Use a calculator. So I'm going to load up Mathematica. This can also be done on a calculator. TI Nspire can definitely do it. The 89 can do it. I'm pretty sure the 84 and the 83 can do it as well. Going to use the solve command. So typically speaking, the solve command is used to solve a single equation or inequality. However, with a slight manipulation, you can use it to solve systems. So we're going to type in the two systems, or the two equations. 2x minus 6y minus 3z equal to 0. Now, with Mathematica, if it's a test, so you know something equals 0, it's a double equals. Right, so we're doing a test for equality, not saying I'm defining this to be 0. Double ampersand. Now type in the second equation. And if you had multiple equations in your system, you would just type in each equation separated by a double ampersand. I think you can also put them in braces and separate them with commas. I think. I happen to know this method works, so it's the method I'm sticking with. Once you have all of your equations in, comma, now you need to tell it what are we solving for. So this is going to have to go in braces. Solving for x, y, and z. Now just hit Shift Enter to execute. Right, it's going to say equations may not give solutions for all solved variables because you have more unknowns than equations. So they tell us y is negative 2x over 3, z is 2x. That means x is a free variable. X can be whatever you want it to be, with one exception. Can't be 0. What happens if x is 0? Then everything's 0. Well, that's just the 0 vector. That is the trivial solution. Obviously, the 0 vector is perpendicular to these two vectors because the 0 vector is perpendicular to every vector. So we ignore that one. Also, it's not unit, right? So we pick x to be anything we want except for 0. What I'm going to do is come back over here. I think that was it, right? Negative 2x over 3 for y and then 2x for z. Hope my memory didn't fail me. So that's the solution to the system. We pick x to be whatever we bloody want it to be. I hate fractions. I'm going to say x is 3. That would make y negative 2 and z 6. That's one vector. I can easily find a second vector by just flipping its direction, right? Multiply it by -1. However, that's not what we were asked for. We were asked for a unit vector. Now we just need to find a vector of length 1 in that direction, or its opposite direction. Again, both answers would be acceptable. Remember, unit vector, you just take 1 over the magnitude of your vector and then multiply by that vector. So it's what, 9, 4, 36. Oh, that's very nice. That's root 49. So there's one such vector. 3/7, -2/7, 6/7. The other possible vector would be -3/7, 2/7, -6/7. They would both be acceptable answers. But those are the only two unit vectors. No matter what you let X be, when you find a unit vector in the direction of that chosen W, and you fully simplify it, this is the form you will get. 3/7, -2/7, and 6/7.
You got like the city X was free. Is there a situation where like X would not be free?
Yeah, but then one of the other ones would be, right? So the idea here is two of them are always going to be written in terms of the remaining one. It's just how do you want it to be, right? Which one do you choose to be or free? Mathematica chooses the simplest one to be free. Questions on the dot product? Excellent.